Florian, you are up first, and Juliette. So I will let you, and I'm sorry that I did not get your summary pasted in here. I apologize for that. That was neglectful of me, but the screen is yours.
Hey, Juliette, if you want to launch.
Sure. Is it working?
Yes,
That's
it's
great.
good.
Yeah.
Ah, great.
Wonderful.
I was nervous about that.
Yeah. Okay, so well, thanks again for the invitation. We will talk today, Juliette and I, about the image project, image that's for accessible internet graphics via audio and touch. And it is a project by the Shared Reality Lab, McGill University, and we have partners. Hang on, let me just do one thing. I wanted to post actually a couple of links so that whenever we get to that point in the presentation, you can look them up. Here we go. Yeah. So we have Image has two partners, Gateway Navigation and the Canadian Council of the Blind. And if you could move to the next slide, Juliette, thank you. From Gateway Navigation, we work with David Brown, he's the director. And I also shared with you the link to Gateway Navigation, where you see how our partner is featuring our project, and there's also an opportunity to actually support us there. It was David Brown, Jeremy Cooperstock, who got together, and that points us already to the team to apply for initial funding. And we are now at the end of our first funding round. We were a little bit unlucky because we got funding for 2 years, and then because of COVID, they cut it down to 1 year. So we had to squeeze a 2-year project as much as possible into 1 year. We didn't completely succeed with that, but we got very, very far. We got far enough so that we managed to get more funding, and we are pretty confident that we can keep on running with this. So a little bit about our team. The whole project is run by Jeff Blum. He's the technical project manager and also put a lot of ideas into the technical architecture. Our technical architecture lead is Juliette Regimbald. She will tell you everything about the architecture of Image. We have Cyan Kuo. She's our usability and UX lead. I am the spatial audio lead, Sonification lead, and we also have Young Jae-yo, who is the haptics lead. Image is not only about sound, it is also about touch, and it is to cater to the two main modalities of the main population we try to serve, which are blind and low vision users. And the head of the Shared Reality Lab is, as I mentioned, Professor Jeremy Cooperstock. We have also 14 additional team members that are not listed in here, and many students also join our project through the course of a year. Okay, next slide, please. Thanks. What is Image? So Image is first and foremost a zero-cost Chrome browser extension. So this is all about creating experiences based on the browser. And our first goal was to make photos, charts, and maps accessible through a browser extension. And the public beta is available on the Chrome store. If you search for image extension by Shared Reality Lab, you will find the extension that you can install, and how this extension then helps you to get the experiences that we create, the audio haptic experiences, probably mostly audio. We will explain you in the next slides. Okay, so why would you want to use that? I mean, blind and low vision users, they of course already use screen readers. There is alt text, either manually entered or automatically generated. Since not so long ago, there is also JAWS Picture Smart, which is an AI-powered automatic audio description of images. It is maybe a little bit more like alt text, automatically generated. And there's also voiceover image descriptions. So far, these are mostly text-based. They largely focus on the content of graphics, not so much the feel of it. And image does not aim to replace these tools, because these tools are in part very, very popular and very well integrated in accessible workflows. So this is what we offer is just complementary, and I think we have designed it such that it very, very easily fits in, and you can use it if you want to get more than just the content of the graphics, and maybe dive also a little bit into what this image or this visual content could feel like. Okay, next slide, please.
Yeah, so to sort of just frame a little bit better what I'll be talking about next, I just wanted to show a clip of how it actually would look in the browser, what that experience is like. So basically, any kind of graphics encountered, and then there is something added to the context menu to send a request to the server to get a set of different renderings. And oh boy, it didn't stay at the end of that video. That's nice. So essentially, this experience is really built around being able to have this quick integrated experience within the browser. But in order to do that, we have to actually get all the data about these images and sonify it. We have to get not only the raw graphic data for photographs, but also various kinds of embedded data for maps and charts, since most embedded maps are unfortunately not, or fortunately, depending on how you look at it, just raw images. Each of these different types of graphics have very different kinds of data and different meanings that may be useful to someone encountering them on the web. And we also, of course, need to transform these into various audio and audio haptic representations live, and to get the response quickly, while also needing to add to really any of this as needs change, and we get feedback from users that, oh, well, actually, no, it's very important for us to do X, Y, and Z. So we need something very flexible as well, which sort of leads to us structuring the process like this, so that graphic is encountered, and we can extract data directly from that. So information about the graphic itself and information stored on a web page around it. But also we need to extract additional information, since that's typically very, very sparse. So using machine learning models and other third-party services wrapped into these generic processes that we have called preprocessors, we can get more of this data about the different assets that are encountered or that a user would encounter. And that additional data is used to augment what is available directly on the web page. And all of that are passed to a set of handlers, where each of them attempt to create audio and audio haptic data from the images. Not all of them succeed, and not all of them run on their own. So they may benefit from other kinds of services that do tasks, specific tasks in parallel that need to be replicated across a variety of different handlers, things like TTS or that are really very common. And these handlers are used to produce a different set of renderings, each one focusing on a different aspect or a different presentation of the graphic, so that ideally, if you have enough of them, the information the user is actually searching for will be presented in an appropriate way. So these preprocessors end up running in a sequential order, passing data from one to the other, so that they can build up additional information as they run. So one may identify this a graphic that is sent from the client as being a photograph, and then other preprocessors that can only run for photographs or cannot run for photographs are able to appropriately respond to the situation. And after they run and do whatever they're capable of doing, then the various handlers that have been implemented are able to run in parallel to try and produce as many renderings as are possible given the information about the image that was collected. So currently, the way that we approach the actual task of creating audio within the handlers we've created is that we have each one collect that data coming from the preprocessors and then create an audio rendering using a text-to-speech service to create create speech representations of labels, and then a running super collider instance to create all of the non-speech audio effects that Florian will talk about much more later. All of those behind different responders that are tied to specific kinds of tasks. So one might be best at showing, handling the data from a photograph, but the others might be better for a certain kind of map. But all of these pull from a common set of functions and synth definitions, which are used to create a common sort of audio experience across these. And this is just the way that we do it because all the handlers run independently. Something other than Super Collider can be used as another third service to create the audio, or it could be integrated within the handler itself. So there's a lot of flexibility here, and something that we're planning on doing is really consolidating the roles of these different responders so that more of that work can be more of the work of determining what information is important and how to appropriately create the sonification can be controlled from the actual handler side rather than needing to be split out into a second software component running in Super Collider, which will ideally make it a lot easier for people to prototype new experiences given different kinds of data and user needs that need to be addressed. So I'm going to turn over to Florian now to talk a bit more about the actual sonifications.
Okay, thanks, Juliette. Yeah, so the spatial audio synthesis in Super Collider we do in higher order ambisonics. I don't know if you're familiar with higher order ambisonics. Bruce, I also see this rectangle, but so far it hasn't covered, I think, any important visual information. So higher order ambisonics is a way to represent spatial audio. And what we are really aiming for is to make the audio as immersive as it could possibly get. Our intermediary synthesis is based on 25 channels, and you see in this pyramid of fancy shapes, you see the directions, the audio directions of these 25 channels. And then, of course, we don't deliver 25 channels back to the browser, but what we do is we fold it together over head-related transfer functions, also known as HRDFs, which you can think of as audio filters, and the result is binaural audio via headphones. So the idea is if you listen to the audio output of the image sonification that arrives at the browser, then you should get pretty immersive audio with lots of spatial features, and we can use these spatial features to actually transmit information about whatever we want to represent. Next slide, please. So in this spatial audio representation, what you see here, what we usually do, but it's not the only possibility, is that we kind of cut out a virtual screen, a virtual audio screen in front of you from the 360 audio that we have all around, and also with elevation. We just define a virtual screen from, say, minus 45 degree to plus 45 degree azimuth, and minus 45 to plus 45 degree elevation. And within this, if you will, audio canvas, we can then place all sorts of objects, and I will speak a little bit more about these objects in the next slide. But before that, I would just like to mention the audio synthesis we do in non-real-time mode in Super Collider, and what is the advantage of this. We can create with all the information that we get from the preprocessors that are many of them are using say artificial intelligence or machine learning to extract information from the images. With all this information from the preprocessors, we create scores, and then we execute these scores in non-real time. That means that a sonification of that lasts, say, 1 minute, or could even be longer. I mean, you always have to be careful with the length of sonifications, but in this case, it's auditory display, it's audio experiences, I would say. These synthesis can be completed within seconds. So the moment you make a request from your browser extension, it usually really only takes a few seconds to send this information to the server. On the server, the whole experience is synthesized and assembled and sent back to the browser. And then within a few seconds, you usually can listen to the results. Next slide, please. The results, the audio experience, the auditory display is to some degree also navigable. Although we actually deliver audio files, and the reason why we decided to deliver audio files and not make this audio synthesis in the browser was also for accessibility reasons, because an audio file can certainly be played back in an accessible manner on all sorts of browsers and websites, if these browsers and websites just simply obey accessibility standards. So that was the reason why we decided to actually make the complete audio synthesis on the server. But we wanted at the same time to provide some possibility to navigate the content. So what you can actually do now, you can break down this audio file into sections, and we have, Juliette has created this great drop-down menu that allows you to jump from one section of the audio file to the next, and each section is typically prefaced with a little bit of text-to-speech synthesis announcing what you would hear. And the next slide, please. I also wanted to point at one feature of how we use text-to-speech synthesis. Juliette has shown before that the text-to-speech synthesis is a service that is called before the whole audio experience is synthesized and assembled. The reason why we do that is that we want to use text-to-speech audio synthesis with spatialization. So what you see here is basically a rectangle that represents some sort of visual content with 3 different types of shapes in it. And we basically say what the shape is, where the shape is. So we use text-to-speech. That's something that has always been of interest in the auditory display field, is how to use audio in a deictic way to point at stuff, because in a visual representation you can share knowledge by pointing at what you're interested in or what you want someone else to pay attention to. In audio, this is usually not so easy, but we have here spatial audio in very, very high spatial resolution, so we can actually also use text-to-speech audio description and say things where they are to make the experience better, and to also actually deliver more content, more information about the visual images that we convey through sound. Next slide, please. Okay, and here we are ready with the examples, and I invite you now to go to the links that I have shared in the chat, and that would be the last link. If you click on the last link, you should arrive at the image website where we have these examples, and we have these examples as pre-rendered audio files, so you don't need to install the browser extension to be able to get a glimpse at what we are doing here. And what you can hear here is basically one sonification of an indoor photograph, and the next example will be one audio representation of an outdoor photograph. Next slide, please. Yeah, maybe take a minute or two, everyone, to just listen to these 2 examples if you have enough time, and then we could later, after that, we will wrap it up quickly, and maybe we can talk a little bit about the image architecture, the image experience. And maybe before you listen to that, what you will hear is objects, but also outlines of shapes that have been recognized through AI and machine learning in these images. So maybe I would say like, I'll pause now for about 2 minutes, so you can very quickly all listen to these examples, ideally with headphones. If not, just you should still get a pretty good spatial impression.
So, Adrian, we are getting short on time. We have one more presentation to do yet today. And so I wanted to see what would you like us to most experience to wrap up here? Would you like to take a few questions
okay,
at this point?
Then if this is the case, I would say, Juliette, maybe you can just go to the next slide. I'll wrap up in 30 seconds, and then we just have a little bit of Q&A if that's possible. Yeah.
Okay.
Just to say, we also work on charts and graphs. We have already one chart prototype. We also have already one prototype for maps. So we can actually also through spatial audio indicate points of interest in maps. And maybe if you can go to the next slide, Juliette. We also want to use spatial audio and outlines and the possibility to represent lines through audio that really trace objects in space. We also have some prototypes that we have already pilot tested for maps and metro lines. And that was quite exciting. We could test it with 10 blind and low vision users in Canada. They would listen to the metro maps of Vancouver, Toronto, and Montreal. And they said that they got a pretty good sense of some places they knew and some metro lines where they approximately knew the layout. And also said like, and it would be so interesting if this was a way that could also allow me to learn about the layout of metro lines and subway systems in other places. So this is something that will also come soon. Not only metro lines, but also neighborhood streets with spatialized sound from a bird's eye map type of perspective. And I think that's it. Next slide would be already the Q&A. Thank you very much. Yeah, and maybe you can listen after the chat and get back to us.
If you we can also, I can leave this open and or we can make arrangements to get together again. So I think this is super interesting. Questions?
I see actually already some questions. Maybe I'd very quickly go to the questions that have been posted in the chat. How is accuracy assessed when adding audio or audio and haptics? So we cannot speak so much about haptics. That would be our colleague Yang Cheo. But these are like really design questions that we try to address through iterative design and participatory design. So we have various participants in Montreal, but also across Canada, who constantly give us feedback. We also identified that photographs are a little bit less sensitive with respect to the accuracy of the images, the accuracy of the content, and that we convey. But there are other types of visual content like line graphs and say stock charts and so on, where it is very, very crucial to really very precisely convey the content, and of course also any scientific charts and plots. That's why we often also try to make good judgment about where we use non-speech and for which purpose. For instance, to just communicate trends, and that we also have text-to-speech where we can, for instance, say very precisely what is the actual amount or what is the actual number in a certain graph, so that we can also provide the necessary precision if needed. Then we have what aspects of the image controls the pitch and the density of the sounds. What is the non-spatial mapping? Okay, so non-spatial mapping we use. One thing that has also been very early in the ICOD community, very much researched, is also some sort of say natural mappings like a low pitch and high pitch, and what are the associations that go with that. And so that we apply that, of course, also to the images where we try to associate with higher pitched sounds. Or so I would say, like we try not always to have like fully pitched sounds, like instrumental sounds that can be a bit annoying if you need to listen to that for a long time, but maybe some sounds that are just some sort of a pitch range, I would say. And then again, like high frequencies associated with up, high in the image, and low frequencies low down. So that's so much about the non-spatial mapping. But I would say, like, we still have many iterations to go to improve on our sound design. But this was just to put an architecture in place and some prototypes in place that we can test with our participants. Are handlers people? No, handlers are not people. They are software units, software functions. And Juliette, you can probably say much more about what handlers are.
To just briefly get to it, it's any kind of running software that is set to respond to HTTP requests containing the data from these preprocessors, so data on the graphic that was encountered, and is able to produce some sort of audio or audio haptic experience that can then be sent to the browser and experienced by a user given whatever hardware is available for them to use. I think that's the briefest way I can put it.
If I can say one more thing about that, is that really the idea of the architecture, or the idea of the sound synthesis, was to create something that is as general as possible, but yet is already capable of creating a concrete experience. So Juliette could probably say much more about the fact that from all the architecture that she presented, many of these units are running, are kind of contained software units, software containers on a server that could be swapped out while the whole architecture continues to be live and can still continue to serve the browser extension through which the user gets the results. So there is a great deal of work that went into the architecture. Also, higher order ambisonics sound with this high spatial resolution. Ideally, I mean, you certainly know about Dolby Atmos, Apple Music, spatial ways of delivering audio content. This is very much en vogue these days. So with higher order ambisonics, particularly fifth order ambisonics, we would be capable to really deliver very rich content later on, also through personalized HRTF or head tracking to keep the audio image persistent. So to create a really high quality audio experience with a good spatial component. We get really good feedback from our blind users about spatial audio and binaural audio. That's always very exciting to hear that they experience it as rich